Unit 7, Design of columns. Okay, design of column. So now yesterday I have given you the homework to solve the problem. I hope you have solved the problem. Okay, and one notice is there regarding that I want to tell you regarding the assignments. If the size of the assignment is large, then you can compress it. Okay, online also you can do it on Google. To reduce the size of the assignment and then upload the assignment on the given links only. Okay, and now this time I think up to assignment number 4 I have given to you the links. So today or tomorrow I will give you the links to the remaining assignments also. So accordingly upload the assignments. Okay, if the size is bigger, then reduce the size, you can compress it. So now today we will move into this chapter, that is design of column. So what is the meaning of column? Okay, so this member, nothing but column, a vertical member which carries a load along its length is called as column. Okay, a member which carries the load along its length is called as column. So this is the simple definition of the column. So generally this member, so if I draw the axis of the column, then this is the axis of the column. Okay, this is the axis of the column, and column always carries this vertical load. Okay, so the length of column, so this is nothing but the length, this dimension we called it as a length. Okay, so length of the column, so you can say that this is of the column. Okay, so column always carries a load along the y-axis, or you can say along the axis parallel to its length. And what is the length of the column? So this dimension, it is called it as a length. Okay, and this we can show it as this is the length of the column. Okay, so this is nothing but length. And the cross sectional dimensions, if I show the cross section, then so this may be the cross section of the column. Here itself I will show about this. This is the cross section of the column. This dimension, we call this dimension as B. Okay, this is the width of the column B, and this is the depth D. Okay, so cross section of the column is B and D. Okay, and the length of the column we generally call it as L, length of the column. So this is the column. Okay, so now normally if you see, the columns are actually loaded. Okay, but sometimes what happens, the column is not perfectly actually loaded. Now suppose if I show you here, this is the column. Okay, again uh, this is the axis of the column. Okay, and if your load is acting exactly at this point, okay, and if your load is acting exactly at this point, okay, then it is concentric load. Okay, it is not the eccentric load. If your load is acting in this way over here, this is your load P. Okay, then the stresses developed in this column are only the direct stresses. Okay, then only the direct stress is developed in the column, and that direct stress sigma, it can be calculated as P by A. Okay, if you see, the eccentricity is 0 over here because the line of action of load is perfectly coinciding with the axis of the column. So if I show you this thing, so this is nothing but your axis of column. Okay, this is your axis of column. So all these things we need to consider in which manner the load is applied on the column before designing the column. So this type of load, this is says that this we can say as a concentric load. Okay, So eccentricity is 0. So in this case, I can write here eccentricity is 0. Okay. So in this case, your bending stress developed in the column is 0. So sigma b, that is your bending stress. Okay. So bending stress is 0 here. Because why it is 0? Because formula for bending stress sigma b, it is m by z. And m by z, m is nothing but it is p into e divided by z as it is. As eccentricity is 0, this stress becomes 0. Okay, so this is in the case of this concentric load. Okay, now if you see the eccentric load, so this is the direct stress developed in the case of concentric load. Now in the case of eccentric load, what will happen? Now suppose if I draw the column over here, so this is the column. Again, this is the axis of the column. I will draw the axis of the column. Now you imagine that the load is not acting now. So now the load is acting here somewhere. Now in this way. Now suppose now here load is acting. Okay. So if load is acting here, now if I give you the names, So suppose this is load P. Okay. This is load P. Okay. Then as usual, this is the axis of the column. Okay. This is nothing but this is axis of column. Axis of column. Now if you see, this load is not perfectly acting. This load is not perfectly acting along the axis. Okay, it acting from some distance. Okay, it is not exactly at the axis. So what will happen due to this load? Okay, so what will happen due to this load? So now suppose if I tell you that due to this load, here if I tell you, so this is the eccentricity E. This is the eccentricity E which is developed, okay, from this point, from the axis to this load P. This is your eccentricity E. Now what will happen due to this P load? The direct stress gets generated as well as the bending stress will be there. So if due to this load P, direct stress sigma, it gets generated, it is P by A. And also what will happen, this load P will generate a moment along its axis, along this axis, and that moment will be forced into perpendicular distance. Along this axis the moments get generated, and that moment is P, that is force into the distance is E. So the moment along the axis will be, it generates a moment along the axis, and that moment is P into E. Okay, so now due to this moment, now bending stress will also get generated, and that sigma b, that is the bending stress sigma b, it is nothing but it can be calculated as m by z. So when a column is eccentrically loaded, we can say that this column is the eccentrically loaded column. So I can elaborate here, the column when the column is eccentrically loaded, is eccentrically loaded eccentrically loaded, then then direct and bending the direct and bending stresses are induced induced in the column. Okay, so this is the important thing you should know. When the load is eccentrically acting, then direct and bending stresses are induced in the column. But when the load is concentrically acting, then the eccentricity is 0. So only direct stress is acting. At that time, only direct stress is present over there. Okay. So how it is possible now? How we are saying that the direct stress and bending stress both are applied. Now I will elaborate this figure only from this surface. Okay. Now I will elaborate this figure from this surface and I will show you how the direct stress and bending stress is acting over there. Okay. Now if we move to the next board, then here if I draw the line, now this is the line. Suppose this is the top surface of the column. Okay. Then then suppose this is the axis of the column. Okay. This is the axis of the column. And now here the load is acting over here. So this is the load P. Okay. This is the load P. Now this is your centroid somewhere here. So it is acting at a distance E. Okay, so this is your eccentricity E here. This is your eccentricity E. Now what will I do? I will apply equal and opposite force P here. Okay, now suppose now if I do in this way. So suppose now I will apply P a force here. Okay, I will apply a force here P, and to neutralize that force again I am apply a downward force P also. Okay. So what I have done, I have applied the force P. Okay, and to neutralize, so sorry, I will draw it. It is not properly visible, so I will draw it again. So if upward force is applied over P, okay, and so to neutralize this I will apply over here a downward force P. Okay. So now if I give the name, this is also P. Now if I give the name, then you can see that this is also P and this is also P. आणि आपण असं करू शकतो ना, if I apply upward P at the same point, if I apply downward load P, then the resultant load at this point will be zero and the equilibrium will get maintained. Okay. Now if you see this mechanism which is found over here. Okay. Now if you see that this P and this force P will form a couple. Okay, will form a couple. So this P and this force P, these are the unlike parallel forces. These two are the unlike parallel forces, and these two forces are separated by a distance d. So these two forces will produce a moment. Okay, and moment of couple, how we can calculate the moment of couple? So moment of couple, it can be calculated as one of the force into distance or lever arm. Okay, so one of the force is P into lever arm is E. Okay, so what will be the resultant? Now if I show you by drawing the diagram again, now again if I take the diagram, if I draw it the surface, this is again the column surface. Okay, then this is the center line of the column, axis of the column, and here now here this P into E. Now see, this arrow is downward, so rotate, take the tip of the arrow and rotate it towards this point, so it is in this direction, and take the tip of this arrow and rotate it towards this P, so it is in clockwise direction. So if you see, this is rotating in this direction. So now if I draw here, then this will be the, then this will be the moment which is getting generated along this axis. Okay, and this moment is nothing but it is P into E. Okay, so this moment M, it is nothing but it is equal to P into E, and this moment caused the bending stress. And now these two forces are getting consumed. See, these two forces are getting consumed in this moment. Okay, we have drawn the moment. Now this force is still remaining, this P. Okay, and that force will remain as it is. Okay? That force will remain as it is, and it will act here. It will act here, and this force is nothing but your P as it is. So now if you see the column, that column is carrying the load as well as it is carrying the moment. Now, if the load is acting in this way at a distance of eccentricity E, if the load P is acting in this way, okay, at a distance eccentricity E, so along with the direct stress, bending stresses are produced. And why those are produced? So if you simplify the force further like this, then you come to know that moment is also getting generated there and force is also there. Okay, so this is why if the eccentric load is there, then direct stress and bending stress both are getting generated. Okay, I hope now this point is clear to you. Then we will go to here. Now if you see that the definition of column is given, so what is the column? So column is a member which carries the load perpendicular to its length. Okay, then you can see that for the column the minimum cover for the column reinforcement is 40 mm. So what is the minimum cover we provide for the column reinforcement? That is the important thing. For column reinforcement we provide 40 mm cover. Okay, and then these are some formulas for the eccentricity. Just now I have told you what is eccentricity. Okay, so the minimum eccentricity for the column, it is taken as 20 mm. Okay, when the effective length of the column is not given to us, then the minimum eccentricity, it should be taken as a 20 mm. You should see this is the minimum eccentricity. The minimum eccentricity should be taken as a 20 mm. Okay, when L effective is not given. So effective length of the column is not known to us, then we should take minimum eccentricity as a 20 mm. Even though you are saying that your load is actually acting and all these things, but in practice, the load is not actually acting. Okay, some eccentricity will be there. Okay, so the minimum eccentricity in the case of column we considered E minimum as 20 mm. Then when the effective length is given, then the minimum eccentricity of the column is calculated as E minimum is equal to L effective upon 500 plus D by 30. So this is the what we can say formula to calculate the minimum eccentricity. So L effective by 500 plus D by 30, and we can calculate the minimum eccentricity by using this formula when the effective length is given, and also we will take minimum eccentricity as 20 mm, and from these two, the value number 1 and value number 2, which is the greater value, that value we considered it as our minimum eccentricity. That value we should always consider as our minimum eccentricity. Okay, so now here the one more thing is that after the comparison of these two, whatever E minimum value you got, that value should be less than or equal to E. E means the eccentricity which is exactly there are eccentricities uh, at the column, and this is your minimum eccentricity, and this is the eccentricity exactly at there at the position. Okay, and this E, it is calculated as E is equal to 0.05 into D. Okay, so 0.05 into D. In this way, this eccentricity is calculated. Okay, so I hope now regarding this eccentricity it is clear to you. We will go to the IS code so that we will see this clause of eccentricity. Okay, clause number 25.4. If we go to the IS code, see over here you can see that this is the clause of minimum eccentricity. Okay, so this is the clause of minimum eccentricity. This clause we need to follow. Okay. So all columns shall be designed for the minimum eccentricity equal to the unsupported length of the column slash 500 plus lateral dimension. Here you can see this, all columns shall be designed for a minimum eccentricity equal to unsupported length of the column slash 500 plus lateral dimension slash 30. Okay, subjected to a minimum of 20 mm. So minimum eccentricity is also given here. They have specified. Okay, if you see, this is here minimum of 20 mm. Okay, so here from this we can say that here E minimum we can take it as a 20 mm, or E minimum is equal to, what is the formula they have given, that is the unsupported length of the column, that is we will take it as a effective length divided by 500, okay, plus it is D by 30, and the greater value of these two is nothing but our E minimum, okay, and the greater value of these two is nothing but our E minimum, and this calculated E minimum should be less than E, so E minimum must should be always less than or equal to E, okay, and how do we calculate this eccentricity E? So E is 0.05 into D. In this way we will calculate this, okay. Now similarly, if you go to the page number 71, okay, then there is a formula for unsupported length of the column. So there is formula for load carrying capacity of the column, okay. So now I will show you that formula also. Okay, so this is the formula. Here you can see clause number 39.3, okay, axially loaded column. Okay. So here this formula is also they have told you when the minimum eccentricity as per 25.4, so that is the clause which just we have seen 25.4, okay, does not exceed 0.05 times the lateral dimension. So that is what I am telling you, 0.05 times the lateral dimension they have told you here, okay. So, and this is 25.4 means just now on previous page, that is I think page number 48, we have seen this formula, okay, this clause. So does not exceed the 0.05 times the lateral dimension, then the member may be designed for the following equation. This equation can be used if this condition is satisfied, and the equation is this much. This is the equation. Pu is equal to 0.4 FCK AC plus 0.67 FY into AC. Okay, so this is the equation that we need to use. Okay. But when we can use this equation, so for using this equation, the condition is that for your syllabus only short columns are there, long columns are not there for your syllabus. And short columns, that too with the axial loading is only there, eccentric columns are also not there, and then you have to design the circular columns for helical reinforcement, okay. The question is asked to me was whether we are going to design the short column or long column. So if I don't tell you, then you remember that for our syllabus only short column is there, long column is not there. First thing. Second thing, we are going to design rectangular and circular columns, short columns, and with in the circular columns with helical reinforcement. And right now we are seeing all the clauses which we are going to use for the short columns to calculate the load carrying capacity of the short column. Okay, and this is the formula. If you see, Pu is equal to 0.4 FCK into AC plus 0.67 FY into ASC. This is the formula to evaluate the design strength, or we can say load carrying capacity of the short column, where Pu is the actual load on the member. Okay, FCK is the characteristic compressive strength, AC is the area of concrete, and then Fy is the characteristic strength in compression, AS is the area of longitudinal reinforcement. AS is the area of longitudinal reinforcement. But when we can use this formula, so there is a condition, your E minimum, your minimum eccentricity should be less than or equal to E. In that case only we can use this formula. Okay, otherwise we can't use this formula. That is specified here in clause number 39.3. Okay, so this is also clause regarding the column which is given over here. This clause also we are going to use, and next there is one more clause which is given, okay. So we will go to page number regarding the transverse reinforcement and longitudinal reinforcement of the column. Okay, so here the detail about the reinforcement is given. Okay, so if you see 26.5.3 column. Okay, so for the reinforcement in the column, we need to refer this clause 26.5.3.1 longitudinal reinforcement. This clause should be followed. Okay, so what does this clause say? So now if you see over here, this point is very important. What is given there? The cross-sectional area of longitudinal reinforcement shall not be less than 0.8% and nor more than 6% of the gross cross-sectional area of the column. Okay. So what is the minimum longitudinal reinforcement? Longitudinal reinforcement means what? Now suppose if this is the cross-section of the column. Okay. If this is the cross-section of the column, then in the column, suppose these are the stirrups. This is the stirrup. Okay. Now, if we provide the bar, suppose four bars are there in the column at four corners. Okay. So these four bars. So these four bars, this is nothing but this is your longitudinal reinforcement. Okay. This is called as longitudinal reinforcement. Okay, and the stirrup which is given over here, this stirrup, this is called as transverse reinforcement. Okay, transverse reinforcement. Okay, or this is also called as or lateral reinforcement. Lateral reinforcement. Both the words are used. Okay, so now this clause is for longitudinal reinforcement. Longitudinal reinforcement means these bars, which we have provided over here. These bars. Okay, this clause is for these bars, and what does it says? It should be minimum not less than, so minimum it should be 0.8% and maximum 6%. So generally we assume 1% of steel in column. Okay, generally we assume 1% steel, in some cases 2%, so we can say that 1 to 2%. Okay, generally we assume 1 to 2% steel in column. Okay, so it is and it is well within the specified range. The minimum still should be 0.8%, maximum is 6%. So we always assume in between 1 to 2% of gross area. Gross area. So gross area means what? B into D. Whatever your cross sectional area is there. Suppose this dimension is D and this dimension is B. Then your gross area AG. AG is gross area. It is B into D. Okay, and 1% of this or 2% of this gross area, we always take the longitudinal reinforcement in the column. Okay, so remember this point also. This can be asked for the MCQ also. The minimum reinforcement in the column should be dash dash dash, and the options will be given to you in the examination. Okay, or for the maximum reinforcement also. So this is the important clause. Then next is this clause is very important. D. Okay, what does it says? In this clause they have mentioned that the the bars shall not be less than 12 mm in diameter. Okay, so what is the minimum diameter for the column bars? So minimum diameter for the column bars is 12 mm. So you cannot provide the bar less than 12 mm for, again it is for longitudinal reinforcement. Remember this. So these bars which we are going to provide in the column, the minimum diameter for these bars is 12 mm. You remember this. What is the minimum diameter? 12 mm. Okay. Again if we move further, then here you can say that for spacing again they have given something. Okay, so here if you see the clause number G, you read all these clause, but those which are very important, those clause are I am telling to you right now. This helical reinforcement and this clause we will see later on while designing the helical reinforcement. Okay, so now the spacing of longitudinal bar measured along the periphery of the column shall not exceed 300 mm. Okay, shall not exceed 300 mm. So this is for the spacing. Generally in columns we calculate the number of bars. Okay, and normally 4 bars and 6 bars or 8 bars. Like in even number we place the bar along the equal distances. Okay, but still the distance should not exceed 300 mm. That care we should take. Okay, so now next thing is, after this now, here they have given you for the clause for the transverse reinforcement. Okay, if you see, the clause are given for transverse reinforcement. So in the transverse reinforcement, whatever may be the these links are there. Links means stirrups. Okay, so the here they have said that the diameter of the stirrup should be what they have said. Just 1 minute. Here, if we go for this, okay. Now here we can see this. You see this point C, 26.5.3.2 and C. Okay, pitch and diameter of lateral ties. Okay, so pitch means the center to center distance between the ties. Okay. Now if I draw the longitudinal section over here, suppose along the length, if I draw the section, suppose this is the column. Okay, so now in this column, suppose the stirrups are provided and they maybe look like this. These are the stirrups which are provided. Okay, so these are the stirrups. So I am along the length I am showing you. Okay, so these are the stirrups. Then the center to center distance between the stirrups. Okay, so from this stirrup, this is the center to center distance. Okay. This is center to center distance between the stirrups. Okay, so this distance it is called as pitch. So center to center distance. Now what they have told to you, the pitch of transverse reinforcement shall not be more than the least of the following distances. Okay, so minimum of the following we should consider for the spacing. The least lateral dimension of the compression member. The least lateral dimension of the compression member means what? Suppose now this is your member. Okay, this dimension is B, this dimension is D. So whichever is the less in between B and D. If suppose B is less, then value of B should be considered. If D is less, then the value of D should be considered over here. The least lateral dimension of the compression member. Okay, that you should take. Then 16 times the smallest diameter of longitudinal reinforcement bar. Okay, 16 times the smallest diameter of the longitudinal reinforcement bar. Okay, so 16D, 16 into D, 16 times, they have told us 16 times. So 16 multiplied by diameter of the bar is D. Okay, or instead of D, we use the notation phi, no? So I will write here phi, so you will not get confused between the top D and this. Okay, 16 phi. So what is the phi? The smallest diameter of the longitudinal reinforcement of the bar. Now longitudinal reinforcement means what? Suppose now in this bar, suppose now in this column, suppose we have provided 4 bars. Okay, suppose the 4 bars are there and each bar is of 12 mm. Each bar is of 12 mm. So what is the diameter of longitudinal reinforcement? 12 mm. So in this case, what will be your spacing? Your spacing will be 16 into 12. Okay, now suppose different diameters are there. Suppose now in this 12 meter, suppose if I add two more bars, suppose here it is one more bar is there, here is also one more bar is there, and the diameter of this bar is suppose now 20 mm. Okay, now total 6 bars are there. Okay, so what should we consider in this case also? They have told us the small diameter. Okay, remember this smallest diameter. So 20 mm and 12 mm, which is small? 12 is small. So we should consider 12 over here. If the diameter of all the bars is equal, then there is no problem. If the various diameters are there, suppose the 4 bars of 12 mm, then 2 bars of 20 mm, or 2 bars of 16 mm. Likewise, the reinforcement is there. So out of those, you need to consider the smallest reinforcement, so smallest bar diameter. Okay, and in no case the spacing or pitch it should be 300 mm. Okay, so in no case it should be 300 mm. So this is regarding the pitch. Now the second clause, if we move on to the second clause, this clause. So this is for the diameter. Okay, and what they have specified, if we read this, the diameter of the polygon links or the lateral ties. So these are called as stirrups or lateral ties. Okay, so I will write over here the name also. So this is called as lateral ties. Okay, lateral ties, or this is also called as stirrups. Okay, so I will write here or. Okay, stirrups or lateral ties. So what they have told us now, the diameter of the polygon links or lateral ties shall shall be not less than 1/4 of the diameter of the largest longitudinal bar. Okay, and in no case less than 16 mm. So what they have told us, that you should consider the bar diameter for this link. Okay, so the diameter phi. Okay, for link. So for this link means for stirrups or lateral ties diameter. So it should be what they have said, not less than 1/4 of the diameter of largest longitudinal bar. So 1/4 into bar diameter. Okay, bar diameter in longitudinal direction. In which direction? Longitudinal direction. Okay, in the longitudinal, and this bar should be largest. No case is there, then the this diameter of the phi should be less than 16 mm. So you can provide 6 mm links lateral ties, 8 mm lateral ties, 10 mm lateral ties, or 12 mm lateral ties. You should take 1/4 of longitudinal bar diameter. Okay, largest longitudinal bar diameter. Now here if I come to the same example now. Okay, now suppose, now again see here the same example B and D. So 4 bars of 12 mm and 2 bars of 20 mm are there. Now we have to fix the diameter for lateral links. So what we will do, which is maximum, 12 maximum or 20 is maximum? 20 is maximum. So we will divide this 20 by 4, 1/4 they have told us. So 20 by 4, what is the answer? 5. But in practice 5 mm bars are not used. So we can round up that 5 to 6. We can take 6 mm bar diameter, or we can go for 8 mm bar diameter. Okay, so in this way we have to uh, provide the transverse reinforcement for the column. Okay, so now this much introduction is sufficient. So now we will move on to the numerical, so that you will get the idea to how to solve the problem. Okay, so we will solve the numerical. So first of all, we will take a simple problem. Okay, so in that problem we are going to design the column, and after that you will come to know how to use the formula and all those things. Okay, so write the problem now. Okay, so the problem is, design a short axially loaded square column 500 by 500 mm. So FCK is 20 Newton per mm square, comma FY 415 Newton per mm square. Then P is given as 2000 kilonewton. Therefore, PU is equal to, ultimate load is equal to 1.5 into 2000. Okay, so what is the value? 1.5 into 2000, 15 गुने 30. So it is 3000 kilonewton. 3000 kilonewton. So here in this problem, L effective length is not given to us. Unsupported length or effective length is not given to us, or they have not specify any condition for the effective length. Okay, so we will take here the E minimum directly as 20 mm. So here effective length effective length is not given. Okay, so therefore we should consider minimum eccentricity as 20 mm. If effective length is given, then you have to see that you should use L effective divided by 500 plus D divided by 30. Okay, you will get one value of eccentricity. Then the second eccentricity is 20 mm, and whatever may be the maximum value in these two, that you should take as your minimum eccentricity. And why do we always consider this minimum eccentricity? Because in this world there is no column exist which is perfectly axially loaded. Okay, so there may be some eccentricity exist. So here we are considering E minimum is equal to 20 mm. Okay, now calculate the actual eccentricity E. So the actual eccentricity E is, okay, so the eccentricity eccentricity E is equal to, it can be calculated as 0.05D, clause number 39 point something, which we have already seen. Okay, so I will put the value. So it is 0.05 into D, it is a square column 500 by 500. So it is 500. So what is the answer? 5 into 5, 25. Okay, so two zeros, two zeros. So 25 mm. So this is your E. 25 mm. So here we can see that eccentricity E is less than E minimum. So here we can use this formula. Pu is equal to 0.4 FCK AC plus 0.67 Fy into AS. Okay. So this formula we can use. It is given in clause number 39.3, page number 71. Okay. So now we will go to here. Your E minimum, so E minimum, it is less than E. Okay, I have already told you E minimum should be less than or equal to E. Okay, so therefore according to clause number 39.4, clause number 39.3, page number 71. Okay, so clause number, you should write down these things: 39.3, page number 71. Pu is equal to, that is ultimate load carrying capacity of the column, which is equal to 0.4 FCK into AC is equal to 0.4 FCK into AC. This formula is also given in the IS code on page number 71. On page number 71. Okay. Then plus 0.67 Fy into ASC plus 0.67 Fy into ASC. 167 Fy into ASC. Okay, so these things are given in the problem. So we know the gross area of the column. We can easily calculate the gross area. So gross area is 500 by 500. Okay, so this is our gross area. So I can write over here. This AC is nothing but, I will tell you what is AC. So this AC is nothing but, it is area of concrete. AC is nothing but, it is area of concrete, and ASC, it is equal to, it is area of steel. It is area of steel. Column always carries compressive load, so here the area of steel in compression, that is ASC, is the area of the steel, and AG is nothing but, AG is the total gross area of column. Okay, I will write here gross cross sectional area of column. Gross cross sectional area of column. So this AG value is known to us. So AG is equal to gross cross sectional area. It is 500 by 500. Okay. So we know that the total gross cross sectional area is nothing but area of steel plus area of concrete. Okay. So total gross cross sectional area is nothing but, what we can say, total area of column. It is nothing but area of steel plus area of concrete. So now if I put here 500 by 500, I can put area of concrete in terms of area of steel. Okay, so therefore here I can write 500 by 500. Okay, this is my gross area. This is my gross area, which is equal to area of steel plus area of concrete as it is. So therefore, if I write the equation for area of concrete, then area of concrete will be, I will subtract this term. So it is 500 by 500 as it is. Okay, and minus area of steel. Okay. So minus area of steel. So put this value of AC in this equation which is shown above. Okay, so put this value of AC in the equation which is shown here, and this value will be in terms of ASC. So here is also AC, here is also AC. PU value is already known to you. Zero point 0.4 is constant. FCK value is known to you. For AC, you are going to put this value which we have calculated over here. Then 0.67 is constant. FY value is known to you. Then ASC. Okay, so ASC is what? ASC we need to calculate. ASC, keep it as it is. So if you solve this equation, then you will get the value of area of steel. Okay. So now next, what I am going to do now, here PU is 3000 into 10 raised to 3 Newton मध्ये घेतलेला आहे, which is equal to 0.4. FCK is 20 into, what is the formula? AC. So AC will be, I can write over here, it is 500 by 500 minus ASC. Okay, 500 by 500 minus ASC plus 0.67, then FY is 415 into ASC as it is, okay. So now solve this equation. There is only one unknown, ASC. So ASC is nothing but area of steel under compression, and let me know the value. Calculate this and let me know the value. So please check the answer. I will go with this value right now. 3703.18. Okay. So 3703.18 mm square. This is the area of steel. Okay. So this is the area of steel. Okay. So now after the calculation of this area of the steel, okay, we need to provide the bars for this number of bars and all those things. But before that, we need to check that whether this reinforcement is greater than the minimum reinforcement, because we have to provide the minimum reinforcement. And we just now we have seen in the IS code, so the minimum reinforcement in the column should be 0.8%. Okay, the minimum reinforcement in the column must be 0.8%. So that we need to calculate first for the minimum reinforcement. So ASC minimum for column. Okay, so we know that ASC minimum for column, area of steel, this is minimum for column, काय घेतो आपण, which is equal to, it is 0.8% of gross cross sectional area, gross cross sectional area. Therefore ASC minimum, ASC minimum is equal to, it is 0.8 divided by 100 into gross area. Gross area is nothing but it is 500 into 500. Calculate the value and let me know the answer. So the answer is 2000. So now see 2000. So minimum reinforcement required is 2000. So what is the minimum reinforcement which is required? Minimum reinforcement required is 2000, but we are providing the reinforcement, we have got the value 3703.18. Okay, so now for this reinforcement of 30, so adopt the area of compression reinforcement as 3703. Okay, this is the area of your compression reinforcement. Now assume certain bar diameter and calculate the number of bars. Okay, so what I will do now, here I will write adopt ASC as 3703.18 3703.18 mm square. This is the value of ASC. Now I will assume certain bar diameter and I will calculate number of bars. So we can assume it now. Now the area is round about 3000, 3500 now. So we can go for 25 mm bars. Okay. So here I will write assume 25 mm bar diameter. So we have assumed 25 mm bar diameter. Then number of bars is equal to what was our area? It is 3703.18. Okay, so 3703.18 whole divided by pi by 4 into 25 square. So let me know the answer. 7.5. So the answer is 7.5. 7.5. So we will round up this value to 8 numbers. 8 numbers. Okay. So we are going AS now calculate ASC provided. Okay, what ASC we have provided? ASC provided. What we have provided? So it is 8 into pi by 4 into 25 square. This is the ASC provided. Provided is 3926.99. Okay, 3926.99 mm square. And it is far more than what we can say required. Okay, so now what we will do, this is our longitudinal reinforcement. So here the design of longitudinal reinforcement is over. What we have done, just we will take one short recap what we have done. Okay, so what we have done, we have calculated the minimum eccentricity, then E minimum 20 mm, then we have calculated actual eccentricity. So from that we have decided that we can use this formula to calculate the load carrying capacity of the column. Pu is equal to 0.4 FCKC plus 0.67 FY ASC. In that we put the value of area of concrete in terms of area of steel. Okay, and from that we calculate the area of steel, then we check that area of steel for minimum area of steel, and after it gets satisfied, we have assumed the number of bars, and we have assumed bar diameter, and then we provide number of bars. Okay, so now after this calculate the area of concrete also. Calculate area of concrete. What area of concrete is there? AC. Area of concrete. किती येते काय सांगा मला area of concrete. Total area मधनं area of steel minus करा, you will get the value of area of concrete. कारण एका कॉलम हा कशापासून बनतो? Column is made up of concrete and steel. Total column is made up of concrete and steel. Okay. So it is 246296.99. So it is 2462, then it is 96.99 mm square. This is your area of concrete. Okay. Now after this we will go for transverse reinforcement now. Okay. So transverse reinforcement. What the clause says for the transverse reinforcement about the diameter. Okay. So diameter of transverse reinforcement. Diameter of link. I will directly write here link. Diameter of link, that is the lateral ties, किंवा I will see right here diameter of lateral ties. Diameter of lateral ties. This diameter should be how much? 1/4 into largest bar diameter of longitudinal reinforcement. Of longitudinal reinforcement. Okay, and why we are saying this? Okay, why we are stating it like that? Because it comes from clause number कुठे clause 26.5.3.2 page number 49. Okay, so it comes from the clause. I will write here for clause number 26.5.3.2 page number 48. Okay, so for diameter now I will use the notation phi. Phi is equal to, it is 1/4 into largest bar longitudinal reinforcement bar is 25 mm. So if you do the calculation, it comes out to be 6 point something. So we will nearly take it as a 6 mm. Okay. You can go for 6 mm or you can also go for 8 mm in this case. 6 mm ही तुम्ही प्रोव्हाइड करू शकता किंवा 8 mm ही प्रोव्हाइड करू शकता. You may go for 8 mm in this case also. So 6.25. Okay, so 6.25. Then we can go for 8 mm also and we can go for 6 mm also. It doesn't matter. Okay. So now I will write here provide 6 mm bar diameter. Provide 6 mm bar diameter for for lateral ties. For lateral ties. Okay, 6 mm bar diameter. Now we need to calculate the pitch of this or spacing of the links. Okay, so next is the pitch, or we can call this as a spacing SV. Okay, so first thing, how it is calculated. SV is equal to, again go to page number 48. Okay, again go to the page number 48 of the IS code, and what does it says? Least lateral dimension, first clause. Okay, first clause is, so if we go there, see here, we will go to the IS code. Okay, now in the IS code here, the same thing is given. So for diameter, we have already finalized the diameter. This is our diameter is 1/4 of 25, and we considered it as nearly equal to 6 mm diameter we have taken. Now here, least lateral dimension of the member. So least lateral dimension, so first case SV is equal to 500 mm. 500 by 500 is our column size. Okay. Now 16 times the smallest 16 times the smallest diameter of the longitudinal reinforcement bar. So 16 into, so SV is equal to 16 into, what is the diameter of bar? It is 25. So that is the second value we should calculate. Okay. And in no case it should be, in no case it should be 300 mm. Okay. So in no case it should be 300 mm. So these three criteria we are going to use to calculate the spacing. These three criteria we are going to use to calculate the spacing. Now we will go to our board. So SV is equal to, so SV is equal to first case least lateral dimension. So it is 500 mm center to center. Then in second case the spacing must be SV is equal to, it is 16D, that is 16 into 25, largest bar diameter. So how much it is? 400. Okay, so it is 400 mm center to center, and in no case the spacing should be 300 mm center to center. Choose the least value between these three. Which is the minimum value? The minimum value is 300. Okay, so we will write here provide provide. Okay, how many bars? 8 bars of 25 mm diameter for longitudinal reinforcement for longitudinal reinforcement and and two-legged two-leg 6 mm stirrup about 300 mm center to center, about 300 mm center to center. Okay, and last thing remaining, that is the cross sectional drawing. Okay, reinforcement detail is the last uh, thing which is remaining. So now we will give the reinforcement details. So in the reinforcement details now, first I will draw the stirrup. So this is the stirrup. Okay, then I will draw the bar, sorry, column. So this is the column, cross section of the column. Then here, how many bars are there? 8 bars are provided. Okay, 500 by 500 means it is the square column, near about square column is there. So for more clarity, I will draw the knit diagram. Okay, so first of all, again I will go for the stirrup. So it should look like a square. Okay, so next column, okay, we will draw the column which is outside. So this is the cross section of the column. Now we will draw the bars which are inside. 8 bars we have provided. This is one. I will provide first 4 bars at the 4 corners. So the placing of bars we will decide. 2, 3 and 4. So these are the 4 bars of 25 mm diameter. Then here at the center I will provide 1 bar, 6. Then here 5, 6. Okay. Then at this center also, here also. So total we have provided 8 bars. Okay. Total we have provided 8 bars. Now for 8 bars, now two-legged stirrups are, and this is our stirrup. Okay, so this stirrup we can also modify it and provide this stirrup as. So now if I select the stirrup, okay, this stirrup can also be given. So the provide this stirrup is provided, and in addition to this you can also provide the stirrup maybe in this way also. For these internal bars you can provide the stirrup separately like this also. Okay, so this is the reinforcement which we are going to provide. So if you don't show this stirrup also, then it is also okay. This design is also correct. So in the examination, pay attention over here. This is the stirrup which you have already shown over here, okay, which is already provided. This is the additional stirrup which I have provided, which is not designed over here. Okay. So this, if you don't show this in the examination, then don't worry, you will not lose any marks. Okay, but we can provide the links. 8 bars are there now, so we can provide the 2 different types of links to hold those 8 heavy bars of 25 mm on their position. Okay, so the bars should not divert from their position. So that is also another purpose. Okay, so that is why it is provided. Okay, so now this thing, so this stirrup may you may connect to here, and their link is there. So this is outside stirrup is two-legged stirrup, and for inside stirrup also, now this stirrup is inside two-legged stirrup only, which is connected to one of these four bars. Hook will be there at somewhere here or here, okay, and this will be connected like this only for the four bars. Okay, and this stirrup is it is from outside covering all eight bars. So in the examination, if even though you don't show this stirrup, okay, then also it doesn't matter. If you show the simple reinforcement, then it is also okay. Okay. So now we will give the name to this. So these are the eight bars. If we give the name, so here these are the eight bars of 25 mm diameter. Here we can say 6 mm links or stirrups or two-legged 6 mm stirrups about 300 mm center to center, and then this dimension is 300 mm. Sorry, it is not 300. I think it is 500. Okay. This dimension is 500 mm. This dimension is also given as 500 mm. Okay. So we will show these dimensions. This is 500 from this point, and this is also 500. Okay. So this is the reinforcement details for the column. So the design is very easy. So here you can give the name reinforcement details along cross section. Okay. So these are the reinforcement details along the cross section. So in this way we can provide the reinforcement to the column. So the problem is very easy now. So here our problem ends.